So let us start the problem solving session for the 12th week. I guess it's the last one. We'll have most likely another session where I will discuss kind of I'll try to cover a few questions from the entire syllabus, just as a kind of very short preparation for the final exam you are going to have. But okay, let us focus on the this problem solving session regarding the content of 12th week. So this 12th week contents mostly deal around the wide sense stationary process and white Gaussian noise, and basically the correlation between the autocorrelation function and the power spectral density and how they relate to each other, the nice relationship between them. So we'll try to explore those concepts via a few assignment like questions. Um, okay. So let us look at today's first question. So first of all, it's asked that X to be an white Gaussian noise with zero mean and autocorrelation function, and then it is passed through an LTI system, linear time invariant system, whose impulse response is given as this. So what is the power of the output random process? So basically it mentioned xt has two property. First of all, it's Gaussian, and second, first one we have encountered in the previous session. The second one is kind of more interesting. It's mentioned as white. So what is basically white? So for that I would like to briefly introduce I basically would like to start from the idea of random process. So random process, basically you can see it, there are many ways of seeing it, but the easiest one in the uh, lecture the professor mentioned that you can see it as a random variable which is a function of t, basically that time. So it's if I graphically try to interpret that, so it's like this curve. So this is the time axis here. So basically you are going to sample at any time instant, let's call t1, and if this is a random process xt, so here you are going to obtain xt1. So this is a random variable, you sample it at some another instant t2, then there you got xt2. So these are random variable, and when you collect them all over like as a continuous process, so that is what random process is. So xt is said to be Gaussian. So first of all, when a random process is called Gaussian, so it's called Gaussian. Okay, that will come via a question later. Let us focus on the just as of now. I guess this brief idea will work, that xt is a Gaussian process when basically this xt1, t2, t3, the different samples at those time instant, if they are jointly Gaussian for any time instant, not for some particular choice. So it's not that I choose some few particular time instants and the samples turns out to be jointly Gaussian, then I am calling xt as a Gaussian process. It's not like that. The time instant can be any time instant, and the if the samples are jointly Gaussian, then only I can call xt as a Gaussian process. So I'd like to focus on the white part. So for that I need to again, okay, maybe starting from the third question is a good idea. So I'll first briefly talk about the, sorry about that, I'll talk about the wide sense stationary random process. So xt is said to be wide sense stationary random process. Now this wide sense stationary, this term is important because what does it say? It says that for a function to be wide sense, okay, a random process has, let's say, mean. If I would like to find the mean of the random process, it is expressed as expected value of xt. and when this mean turns out to be stationary in mean, that is a crude way of saying that does not depend on time t. So if this mean of this random process mu x doesn't depend on the time t, then we can call the random process stationary in mean, but we cannot still call it wide sense stationary, because for that it need to satisfy more criteria. So just when a random process satisfy this condition here, mu x, expected value of xt, and this term turns out to be a stationary value with respect to time t, that is it is not depending on the time, so then we call the random process to be stationary in mean. Next we look at another interesting metric, that is auto correlation function. So first I will write the expression for it, and then we'll talk about that. Okay. So it's a function of two time instants, t1 t2. It is given as expected value of x t1 x t2. So you can see, as the name suggests, autocorrelation, you can guess the thing. It basically try to find the correlation between the samples of any random process at two different time instants. So that is why these two different time instant t1 and t2. So we have a random process like this. Let's say this is t1 and this is t2. So we'll have two samples, and we compute the expectation of that over all t1 and t2. So that's why we get autocorrelation function. So we can consider the random process. If I talk about the let's say temperature at a particular day, so as a random process, so how it's going to be, like for example, day 1, the temperature graph is something like this. For day 2 it's like that. For day 3 we have this kind of graph. So this all combined form a random process. So if I every day, let's say I am sampling at t1 instant, t1, so let's call it x1, this is x2, this is x3. So you can see, even if I am sampling at the same time instant every day, the sample points vary, right? So we take all these values and we compute the expectation, so that will give me the autocorrelation function that basically intuitively says about the correlation of the samples of a random process at two different time instants. So you can intuitively have this idea that if this sample instants t1 and t2 are far apart and the random process is changing very fast, then you can expect the correlation between them very small. That means these samples are going to be uncorrelated. On the other hand, if let's say the sampling instant t1 and t2 are very close to each other, and also the random process is varying very slowly, so we can expect a large correlation, because when we move from t1 to t2, the sample doesn't change much, so then we will have some higher correlation. So for a random process to qualify as a wide sense stationary, this thing, this autocorrelation function, which is a function of two time instants usually for any standard random process, this should be equal to the difference between them, that it no longer remains the function of two time instant, it is a function of the difference between them. So what I mean, for a standard random process, autocorrelation function at t1, t2 and t1 plus alpha, t2 plus alpha, this need not to be equal, because you can see here the time instants are different and so does here. But for wide sense stationary random process, this autocorrelation t1 t2 should be equal to t1 plus alpha comma t2 plus alpha, and that is given by t1 minus t2, because you can see the difference between the time instant is here also t1 t2. So it is no longer dependent on the individual time instants, but rather depend on the difference between them, difference between time instants. And a corollary of this you can find, for example, you consider what will happen for WSS wide stationary random process when t1 is equal to t2. You can see this is nothing but autocorrelation function evaluated at 0, and this is nothing but, from the expression of autocorrelation function, is x t square. So what is this? This is the power of this random process, and by the definition of wide sense stationary, this should be constant. So for random process x2 to qualify as a wide sense stationary, the first property is that it need to be stationary in mean, that is basically your mu x is a constant, that is it doesn't depend on t. Secondly, the autocorrelation function, which is usually a function of two time instant, for wide sense stationary it's actually depends on the difference between them, not the individual values. So more importantly, it depends on the difference in the time instant or the shift between them, so that is being captured here. And thirdly, this is actually a corollary of this thing. So since it's a difference between two time instant, when the time instants are same, that's basically equivalent to evaluating autocorrelation function at 0. So you are basically correlating xt with itself, so that gives you the power of xt. And you can see from this expression, this no longer depends on time, it is the autocorrelation function evaluated at this particular point, so it's a constant. So for a random process to be wide sense stationary, all three properties should hold, 1 2 3, so the fourth one is the correct answer here. So with that knowledge of just a moment, okay, so with that knowledge of wide sense stationary, now we move to the part of this white. So white is kind of a more strict constraints, and so when a random process I can even call it white. So that will happen when my autocorrelation function, first of all it need to be a wide sense stationary, of course, and white means your autocorrelation function is a scaled value, the scaling factor can be anything, but more importantly it's a delta function. Sorry, tau I'm writing, so it should be delta tau here. So what does that mean? My autocorrelation function being something like this sort. This has a height of eta over 2, and this is what my autocorrelation function is. So you all know that Dirac delta is 1 when tau is 0 and 0 otherwise. So what does it exactly mean? It means if I go back to the expression of autocorrelation function for wide sense stationary process, it's a correlation of this random process at this time instant t with at t plus tau. Xt x t plus tau. So that is what the autocorrelation function expression says. So now that being 0 for tau non-zero, what does it mean? It means that xt and xt plus tau are uncorrelated for non-zero shift tau. So you can see that is a very strict constant. Like if let's take a practical example, let's have a random process here. So what does it basically saying? Let's say it's t here. So this is xt random variable, and this is a shift of tau, that is t plus tau. This gap is tau here, x t plus tau. So what this random process being wide essentially saying that xt and xt plus tau are completely uncorrelated. That's why its expectation of their product goes to 0, and that is happening for any tau. So let's say if tau is take a hypothetical value 1 second. So I have a random process, I sample it at any time instant, I obtain a random variable, I sample it another time instant which has a gap of just 1 second. So these two are essentially now becomes uncorrelated. So you can see that's a very strict kind of condition, so that random process need to be like let's say the variation should be extremely high, because it is saying that for any non-zero shift, like the random variables are going to be uncorrelated with each other. So we'll obtain only the autocorrelation function is only non-zero when you are correlating a random variable with itself, that is at 0 shift. The moment the shift is non-zero, no matter how small that is, the random variables become uncorrelated. So that essentially implies that the random process is uh, varying it at an extremely fast rate. Of course this is a theoretical case, practically it's very difficult to obtain, because let's say according to the theory here, even if your tau is 1 millisecond, the xt and xt plus tau are going to be uncorrelated. That is very difficult to obtain in practice. So that lead to another thing here. Say I have this autocorrelation function here. So what if I take the Fourier transform of it? What do I obtain? So Fourier transform of autocorrelation function given as follows. e to the power minus j 2 pi f tau d tau minus infinity to infinity. So since you are integrating over tau, it will be only a function of f. So let's call it s f is equal to this. So this is essentially the Fourier transform of autocorrelation function. It has a particular name and it has also mentioned in lecture, of course, but I am not still saying what this is. And similarly, if I take the inverse Fourier transform here, so if I want to go from SF to autocorrelation function, inverse Fourier transform or IFT, so what I will obtain is this. Again integration, but this time of SF, the exponential sign will just change. So now I want to use this inverse Fourier transform expression by putting tau is equal to 0. So what we are going to obtain, let's check that. Remember this expression here, so tau is equal to 0, basically tau is equal to 0 here, so the exponential of 0 it's just goes to 1. So now Rx autocorrelation function evaluated at 0 will just become integration of SF over the entire frequency spectrum. Let's see what it signifies. Autocorrelation function evaluated at 0 is equal to minus infinity to infinity SF df. So this one here is the power of xt, right? And we know from Parseval theorem that whether you try to compute the power in time domain or frequency domain, they are actually same, and here you are integrating over the whole frequency spectrum, right? So I can call it power spectral density, or basically it's a measure of power at every unit frequency. So that is when you, this is the measure, you have this density, when you integrate it over the whole spectrum you obtain the power in the frequency domain, and according to Parseval theorem the power in time domain and frequency domain are going to be same. So that's what the notion is. So when you take the Fourier transform of autocorrelation function, you actually end up having the power spectral density. That's a very useful information. Why I'm saying that, because in context of in context of white noise, we have already seen that the autocorrelation function is given as some scalar times Dirac delta. And what is the Fourier transform of Dirac delta? If I would like to ask, what do you obtain here? So basically the idea is this, the Dirac delta is kind of extreme. So the idea is, if my in the time domain, this is, let's say this is time domain and this is frequency domain. I'm not drawing the exact shape, I'm just trying to get the idea. In time domain, if the pulse is spread, in the frequency domain it's going to be narrow. And if I draw another one here, let's say that pulse is now spread in time domain, sorry, just a moment. Let's say in time domain the pulse become now narrower compared to my earlier this diagram. Then what happened in frequency domain, that basically spread. You can compare this to this to this. So basically whatever time domain operation is happening in times of this width, then frequency domain just the opposite happens. In time domain, if your pulse is spread, in frequency domain the bandwidth shrink, and in time domain you have a short pulse, in the frequency domain you have a large bandwidth. So that's the extreme case. I'm called about pulse shrinking. So Dirac delta is kind of the extreme case, because you know the definition of Dirac delta. It actually has infinitesimally small width and infinite height, right? So its frequency domain representation is going to be spread over the entire spectrum. So that is not able to I'm not able to show here. So that basically means spread over entire spectrum. So for a white Gaussian noise, what is happening is that the power spectral density is eta over 2 for frequency ranging from minus infinity to infinity. That means it can be drawn something like this. So you can see that spectrum is constant over all frequency. Now you think a bit and try to draw similarity of this with something you have encountered in past somewhere. Now what does the concept look similar to? Whose spectrum is constant over all frequency? Actually it is the, if you remember, it is the white light actually. If you see the spectrum of white light, it basically contains all frequencies. So the spectrum is kind of constant over the entire frequency range. So because of this similarity with the white light spectrum, it's called white. That is the name came from white. That basically shows that spectrum is frequency flat, or basically it's not frequency selective. It's not that it has a different value at different frequencies. It's kind of uniform. So it's a uniform spectrum, and that's why it's called white, because it has similarity to that of white light. So for a white Gaussian noise, we see we have this power spectral density eta over 2. Fine. Now next, what is being said? Okay, it has a autocorrelation function 2 delta tau. Fine. And it is passed through an LTI system whose impulse response is this. So now I need to pass this xt through a LTI system here, and I am going to obtain this yt. So to find the power of output random process yt, I need to find this distribution first, and LTI system is having the impulse response of ht here. So let us look at few equations. How? Okay, just a minute. New slide. Okay, fine. So xt is being passed through this LTI system, that is denoted as ht, and we obtain yt outside. So we know the expression of yt here. It's a linear convolution between xt and ht. So xt convoluted with ht, and if I am need to write the expression, it's xt minus alpha h alpha d alpha, integration over that. Now I have to find first the mean of yt. So what is going to be? So since it's said to be a white Gaussian noise, we already know it's a white sense stationary process only. So if I need to find the expected value of yt here, so I basically need to find the expected value of integral x t minus alpha h alpha d alpha. So when I talk about the expectation, the only randomness here is in x. So expectation and integral can be interchanged because they are both linear operator. So we have expected value of xt minus alpha h alpha d alpha, and xt as mentioned white Gaussian noise, so underlying it's white sense stationary only, so its mean is independent of the time, so that we denote as mu x, and since this is a constant it can come outside, so we obtain mu x h alpha d alpha. And you can see, okay, I have not written the limit of integral, now this is the limit. So you can see this is the mean of yt, and as we can see this is also independent of the time, so we at least have this equation, this is stationary in,
Hello.
yeah, hello, you can hear me?
Yes, actually, next at my end, I think there is a issue because I'm in office.
Your voice is breaking a bit, I'm not able to hear that.
Hello.
Hello, yeah, now I can hear you.
Actually, net connection at my end is not so good. Uh,
Okay, okay, okay,
Now I am audible.
yes, yes, you're audible now.
So after that, we have a one more session, right? In which you are going to some of the question which is related to the examination.
Related to the examination, actually I am not uh, okay, by what I mean, basically I would like to summarize the things that have been covered in all this lecture via maybe one questions per session, like that, from every week, kind of these things, maybe a key concept, so like that, because when I say questions related to the main, like, final exam, I really don't have an idea what's going to be there because I'm not involved in any way. So basically I will summarize in the next session whatever being covered in the entire this 11 or 12 week, one two questions per week's contents, maybe like that.
So it's a summary lecture, right?
Yes, 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 kind of summary lecture. I try to explain a few key concepts which might be
I think you
useful.
are also not able to hear me properly.
Yeah, because I am able to hear you only partly. Like some parts are very
There is a
clear.
issue at my end, not at your end.
Okay, okay, okay. Okay, so I am continuing, and if you want to ask some questions, you can also write also in the chat box. I can go through it. So we have already seen that y, that the output of the LTI system, is also stationary in mean. Now we need to check whether the yt is also wide sense stationary not. For that it need to qualify, if you remember, another property of autocorrelation function being dependent on the time shift instead of the individual time instant. So that we need to verify. So for that we need to compute the expectation of yt times y t plus tau. So that is equivalent to computing the expectation. So we'll write what yt is xt minus alpha h alpha d alpha times t plus tau minus, I need to use another variable to keep them separate, h beta d beta. Okay, so this is kind of a double integral where we have x t minus alpha x t plus alpha minus beta h alpha h beta d alpha d beta. Now again, since this part is the only random one here, so we can bring the expectation inside. So this is basically expected value of x t minus alpha times x t plus alpha minus beta h alpha h beta d alpha d beta. So okay, just a moment. So as I was saying, it should be expected value of this. So this one here we can see this is nothing but the autocorrelation function for the x, which is already wide sense stationary. So that is basically the difference between these two time instant, which it turn out to be rx. Sorry, it should not be alpha here, it should be t plus tau. T plus tau plus tau here. So it is tau plus alpha minus beta h alpha h beta d alpha d beta. So you can see this is a integral, double integral over alpha and beta, and therefore the effect of alpha and beta would be averaged out, so only parameter remaining is tau. So this whole thing is a function of tau, function of only time shift tau. So therefore the autocorrelation is also function of tau. So basically that means it's a wide sense stationary process. So these two together here implies yt is also wide sense stationary. Now I'd like to massage this expression a bit. So let us introduce another slide here. So we'll see what we have. We have rx tau minus alpha plus beta h alpha h beta d alpha d beta, right? Or tau minus, okay, I made a mistake here. I'm subtracting this one for this one, so okay, tau plus beta, no, it's fine only. So tau plus alpha minus beta, I make the error here.
Hello.
Yeah, hello. I can hear you now.
Uh, will uh, you just continue the lecture. I will see the recording. If I am left by any
Okay, okay, sure, sure,
lecture, will see the recording lecture.
sure, 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 sure. So we have this expression here. So I would like to make a few changes here. I would like to introduce a parameter alpha tilde, which is basically minus alpha. So by change of variable now I can write tau minus alpha tilde minus beta h of minus alpha tilde h of beta d alpha d beta. So h of minus alpha tilde, this one here, I am denoting as h tilde of alpha tilde. Okay, so this is Rx tau minus alpha tilde minus beta h tilde of alpha tilde h beta. Okay, here should be d alpha tilde d alpha tilde d beta. So this is nothing but the convolution of x with convolution of autocorrelation function with h tilde and h. So that I will write as Rx tau convoluted with h tilde and h. So we have seen that h tilde of alpha tilde is nothing but h of minus alpha tilde. So that means h tilde of tau is equal to h of minus tau. So that means this convolution here, if I write in terms of h only, Rx tau convolution with h of minus tau convolution with h tau, and I take the whole thing to the frequency domain frequency domain or Fourier transform. This convolution will be just simply multiplication, right? So this one here is going to become the power spectral density multiplied with this one. I am keeping blank as of now. H tau, I know that frequency response is given as hf. Now what about h of minus tilde? So h of minus tilde is going to have a Fourier transform. If I write the Fourier transform of that, it is going to be as follows: h of minus tilde h sorry the voice being recorded. Okay, desktop audio. So it's h of minus tilde here has a Fourier transform as follows: h of minus tilde e to the power minus j 2 pi f tau d tau. Okay, let me just change the computation here. Let me start the other way around. We know that hf is the frequency transform of h tau, right? So therefore I can write it as h tau e to the power minus j 2 pi f tau d tau integration from minus infinity to infinity. So I can write the same by making the change of variable as follows: minus infinity to infinity h of, let's say I'm writing it as minus tau dash. So it will become e to the power j 2 pi f tau dash d tau dash, right? So this is what hf is. So if I take the complex conjugate of that h star f, so what it's going to change? This is real, so this is not going to change. This is as it is. E to the power minus j 2 pi f tau dash d tau dash. So this one here is the Fourier transform of h minus tau. You just instead of tau dash you can write any variable. It would be just Fourier transform of h of minus tau. So this one here h of minus tau has a Fourier transform h star of f, and this is a h, this is complex conjugate of h, so it essentially becomes the power spectral density times absolute value of hf square. So now we have this expression here. What is being asked here? Okay, just a minute. So what we obtain here is nothing but the power spectral density of y. So in the question, if you remember, we are asked the what is the power of output random process. So how to obtain the power? We have to first obtain the power spectral density of y, which we have just obtained. Now I will just integrate over the whole frequency spectrum and find the power spectrum of yt. But before that, there are two important tasks here. So let me just introduce another slide here. So we have obtained SYF. This is the power spectral density of Y. This is given as Sx of F times absolute value of Hf square. This is the frequency response of LTI system. And what is SXF? This is the power spectral density of X. So what is the power of y then? Power of y is essentially you have to integrate the power spectral density of y over the frequency spectrum. That's how we obtain. But before that we need SXF and HF. So we are given the autocorrelation function as 2 tau, right? So that implies that the power spectral density of X is going to be just 2 and over the entire frequency spectrum. And what about the HF? So we are given HT as, let us check what we are given, sine 4 pi t over pi t, right? Sine 4 pi t over pi t. So this is nothing but 4 sinc 4t, right? And what is the Fourier transform of sinc function? So if you are given sinc of at, so I'm just drawing the frequency transform here. So it is minus a by 2 to a by 2, and its height is 1 over a. So therefore the HF is going to be uh, 4 times 1 over 4, that is 1, and that is over minus a by 2 is minus 2, that is from f minus 2 to 2. Okay, so xf is a constant, hf is a constant, so that's a pretty easy job for us. Now I have not integrate over the whole spectrum from only minus 2 to 2. So minus 2 to 2, syf is product of sxf is 2 times hf square, which is a magnitude of 1, so basically 1, you have df. So you have 2 times this, so that means 4 times 2, we have the power of random process y as 8. So let us see which one of the answer matches with this one. Okay, so first one matches, so one is the correct answer. So we have a next question. So we have to consider the wireless system xt, which has a particular autocorrelation function, and you have to find the bandwidth which contain 95% of the transmit power. Okay, so we are given xt. Okay, just a moment, system is hanging as of now. What is happening? Okay, it's fine now. So we are given an autocorrelation function which have this following format: 1 over 2a to the power minus a tau. So we can see that it's like it's a wide sense stationary just from that point, because the autocorrelation is a function of time shift only. So if I try to visualize how it's going to look like, so you can see it's kind of symmetric against the time axis, tau axis, but the way you want to see it. So here it has the peak value of 1 over 2a, and when you move both on left and right side, it reduces exponentially with a scaling factor of a. So basically we are asked what is the bandwidth which contains 95% of the transmit power. Fine. So how do we do that? We kind of guess it. So we have this autocorrelation function. We can now just take the Fourier transform. So that will give us the power spectral density, which is a measure of power per unit spectrum. And our next task is to find the uh, spectrum width or the bandwidth where it is 95% of transmit power is concentrated for this particular signal. So that is our job. So for that, we know that when we are given autocorrelation function expression, it is very easy to find the power of wireless signal, right? Because expected value of, just a moment, so if I am to find the power of xt, which is nothing but expected value of absolute xt square, and that is nothing but the autocorrelation function evaluated at the 0th time shift. So you just put 0 in place of tau here, what we will obtain is 1 over 2a. So that is the power of signal, and this should be equal to the power in the frequency domain also, where this is the power spectral density. Now the job is to find the expression of this power spectral density and then put the equation and the bandwidth here to compute the 90% of power. So if I am to find the SXF here, so how do we do it? Basically minus infinity to infinity Rx tau e to the power minus j 2 pi f tau d tau. Now since this is a symmetric function, this integral is divided into two parts, minus infinity to infinity. It takes value 1 over 2a to the power minus a of minus tau, that is e to the power a tau, and then we have e to the power minus j 2 pi f tau d tau, and we have next we have 0 to infinity. In this here we have 1 over 2a to the power minus a tau, since tau is positive in this regime, and to the power minus j 2 pi f tau d tau. So this will make minus infinity to infinity 1 over 2a to the power a minus j 2 pi f tau d tau plus 0 to infinity 1 over 2a to the power minus a plus j 2 pi f times tau d tau. So I'll introduce a slide here. So you can take 1 over 2a common as of now. Now for the first term we have let's check what we have, a to the power my a tau d tau, so it's a minus j 2 pi f, a minus j 2 pi f times a to the power a minus j 2 pi f tau. Just a moment, this integral won't remain here, it would be just minus infinity to 0, then again we have minus 1 over, sorry, plus here, minus of a plus j 2 pi f, and then we have e to the power minus a plus j 2 pi f tau equal to 0 to infinity. So this is 1 over 2a, so this tau evaluated at 0 will be 1, and tau is equal to minus infinity. Just a minute. Okay, sorry about that interruption. So we are considering this thing here, so if we put tau is equal to 0, so that basically become 1, and when I put tau is equal to minus infinity, so essentially becomes 0. So we are left with 1 over a to the power minus j 2 pi f here. Similarly, here when I put tau is equal to minus infinity, it is 0, and when I put 0, it's 1, but the sign changes here, so minus minus cancel out, so we are left with a plus j 2 pi f here. So that will essentially lead to 1 over 2a times a square minus j square 4 pi square f square, and the top we have here 2a. So these two cancel out, and we are left with a square plus uh, minus j square means 1, so 4 pi square f square. So this is what the expression of the power spectral density of X. Now our task is to find the interval. So let's consider 95% of power is contained 95% of power is contained in the interval minus f1 to f1. So what we need to do, we know our total power is 1 over 2a, that we have already obtained from this slide. This is our total power. So we need to find the 0.95% of that where it's concentrated, and for that we need to integrate our power spectral density. So this is the power spectral density we just obtained, power spectral density that we have just obtained. We need to integrate over it the spectrum, which spectrum minus f1 to f1, because we are assuming that in this we are willing to find this value of f1 particularly. So if I integrate the power spectral density over this spectrum, so it will give me where that 95% of total power, because that's what my assumption here is, that 95% of power is concentrated in this interval only. So let us just replace those values here. So I need to introduce another slide. So it's 0.95 divided by 2a is equal to minus f1 to f1 1 over a square plus 4 pi square f square df, right? So I will just take here 1 over 4 pi square common, so that would make it minus f1 to f1 1 over f square plus s square by 4 pi square df. So this is a standard format of what, of tan inverse.
इतने कुछ पता नहीं है.
So you can see, if we just consider this standard equation, 1 over a square plus x square dx, that is nothing but tan inverse x over a. So I'm just replacing the same here. We have 0.95 over 2a is equal to 1 over 4 pi square tan inverse f over a over 2 pi, and these two values minus f1 and f1 here. So next we'll have this 0.95 over 2a 1 over 4 pi square square inverse. Okay, there is one over a involved, if I'm not wrong. Yes, 1 over a should be here. So 1 over a means here it's 2 pi over a, 2 pi over a, and then I'll have 2 tan inverse 2 pi f1 over a. So here we'll have 2 pi here, and then this here should not be. So it's 0.95, this 2 here, 2 cancels out, 0.95 pi is equal to tan inverse 2 pi f1 divided by a. Or did I do a mistake here? 2 pi here. Okay, there should be 2 here. By 2 pi a here, another 2 should be okay. Yes, 0.952 here. So we have this following expression: 2 pi f1 divided by a is equal to tan of 0.95 into pi by 2. That is, so I need to compute that. Let me just use the calculator once. 0.95 into 90. 0.95 into 90. 10 of that is 12.706. So this is 12.706. So from this we get F1 is equal to A times 12.706 divided by 2 pi. Let me just compute this. 12.706 divided by 2 divided by pi. It's 2.02. It's 2.02 A. So the F1 value we are looking for, it's 2.02 A. So our, introduce another slide here. So the bandwidth that contains 95% of power is given as, we earlier assumed it's minus F1 to F1, and then we obtain the value of F1 here, minus 2.02 A to 2.02 A, where A is equal to, we have given in the question, 10 kilohertz. So it's 2.02 times 10, 2.02 times 10 here, so 20.2 minus 20.2 kilohertz to 20.2 kilohertz. So if we call it pass band width, it is 40.4 kilohertz. So this particular spectrum contains 95% of total power for the signal given in question here. What is that? 8. Okay, yeah, this one. So basically we are given the autocorrelation function. So from whenever we are given the autocorrelation function for the wide sense stationary process, it's pretty easy. You just evaluate the autocorrelation at time shift tau is equal to 0. You will obtain the total power. Once you obtain the power, that is same as the power in frequency domain, which is given as the integral of power spectral density over the frequency spectrum, right? And the power spectral density you can obtain by performing Fourier transformation of the autocorrelation function. Once you obtain the power spectral density, you just integrate over a given spectrum, and questions most likely it will be given either the total transmit power or 95% or the 90% or 50%, whatever that is. You need to basically consider a particular spectrum and integrate the power spectral density over that spectrum and equate it with the whatever fraction of power is given, and from that you will get that particular frequency. So that is going to be your answer. For our case, it's the answer is 40.4 kilohertz. So if I look at the options, so most closest one is this 40.45. Actually it might be 40.45 because I have just ignored a few terms after the decimals. If you consider them up to the 3 uh, places after the decimal, then you will obtain maybe 40.45. So with that, let us move to our next question. That is again kind of a refresher slide kind of thing about a binary symmetric channel, and these are the like best kind of question to understand the relationship between the prior probability, likelihood, and a posteriori, which are very fundamental in the receiver design particularly. So Just a moment. হ্যাঁ কে না ও ক্লাস চলছে এখন একটা হ্যাঁ okay, sorry about that. And so we are given, so let me basically draw the diagram of binary symmetric channel, because every time we draw it the things become much more clear rather than this dry mathematics. So binary symmetric channel basically talks about you have two things to transmit, either a naught or a1. So this is the what I am talking about, the transmitter side picture. On the receiver side we have b naught and b1 being received. So basically there are four probabilities. Under the hypothesis a naught is transmitted, you can either receive b naught and you can receive b1. Similarly for a1 also.
In the hello,
Yeah, hello.
it is a last. It is similar like last lecture, right?
Yes, yes, yes. It is similar only. Values are I guess different, but yeah, the concept remains same only. So with a1, what is the probability of being b1 being received? So on the transmitter side, as we probably already know, but just serves as a refresher for you, this is the prior probability of a naught being transmitted, that is 0.75, and this is prior probability of a1, so that is 1 minus 0.75, that is 0.25. So you can see intuitively a naught is 3 times more likely to be transmitted than a1, but this is all about the prior. Then we comes about the likelihood. So what is the probability that b naught will be received given a naught is transmitted? So that is also given here, that is 0.8. Actually what is given is this first, that probability of b1 being received given a naught is transmitted. So this is likelihood p of b1 given a naught, that is 0.2. Therefore p of b naught given a naught is 0.8. Similarly, uh, this one also, probability of b naught given a1 is 0.2, and probability of b1 given a1 is 0.8. So these things are, all of them, they are likelihoods. And then on the receiver side we have this p of b naught, sorry, in the receiver side we have a posteriori probabilities, that after the observation is made, you know whether b naught or b1 is received. Now you want to compute what is the probability that a naught is transmitted. So for b naught there are two chances, probability of a naught given b1 and probability of a1 given, sorry, it's b naught here. Similarly here there are two chances again, probability of a naught given b1 is transmitted, sorry, probability of a naught being transmitted given b1 is received, and probability of a1 being transmitted given b1 is received. So these all are a posteriori probability. So basically you are given this prior here, this is prior, you are given the likelihood. Remember in the assignment question or in your exam the things might be a bit different. Here it's asked about the a posteriori probability, but there it might be the a posteriori probability might be given and you might be asked to find prior, maybe like a posteriori likelihood are given, you are supposed to find the prior, or a posteriori and priors are given, you are supposed to find the likelihood. So basically three of these things are there, prior, likelihood and a posteriori. You will be given the two of them and you are supposed to find the third one, that can go either way. So p of a1 given b1, I won't get into the details because that we have already covered in the previous sessions. I'll just write the expressions here, is probability of b1 given a1 times probability of a1 and the denominator we have probability of b1 given a1 times probability of a1 plus probability of b1 given a naught times probability of a naught. So what is the probability of b1 given a1? It's 0.8. What is the probability of a1? It's 0.75. And here you have 0.8 times 0.75 plus 0.2 times 0.75. Okay, probability of a1 is 0.25 here, so should make the correction. This is 0.25 and this also here is 0.25. So what we are going to get here, 0.8 times 0.25 is basically 0.2. So we have 0.2 divided by 0.2 plus 0.75 into 2 is 0.15. So this is 0.2 divided by 0.35. So that is equivalent of saying 4 divided by 7. Yeah, 4 divided by 7. So the a posteriori probability that a1 is being transmitted given b1 is received is this 4 over 7 here. With that, let us move to our next question, which say that random variable theta is uniformly distributed in this particular interval 0 comma pi by 2. So if I plan to draw the PDF of the probability distribution function of of theta, probability distribution function of theta, so it would be given as 0 pi by 2, and since the area under the PDF is always 1, so the height is basically the reciprocal of the width here, because since it's a rectangular shape, it's 2 over pi. So we are supposed to find the PDF of random variable phi given as tan square theta. So these are also kind of refresher of the previous sessions. We have already seen. By the way, transformation of random variable is actually very powerful tool. So this is no harm in refreshing the concept. So it's if y is equal to hx and the x has PDF fx of x, we have seen how to obtain the PDF of y. So it is basically fx of x at x is equal to h inverse of y and divided by the absolute value of the gradient of y with respect to h inverse y, right? So our fx here, that is p theta, is a constant, so it doesn't really, it's trivial only, it's 2 over pi. So all you need to compute dy dx. Here our y is equal to phi is equal to tan square theta and x is equal to theta only. So if I compute dy dx, that is d tan square theta dx, sorry, d phi, d theta, sorry, it's d theta. So that is 2 tan theta sec square theta, and we have to write the we have to write them in terms of y. So how do we do that? This is nothing but 2 square root of phi 1 plus phi, because x square theta is nothing but 1 plus tan square theta. Tan square theta is given as phi, so this is the result. So I can replace it here. It's 2 square root of phi times 1 plus phi. Of course the range of phi is given as this. So here actually options are not matching, so let me just recheck my calculation once. dy dx tan square theta d theta to tan theta square theta, okay, tan theta is square root of phi only, theta is 1 plus tan square theta, that is 1 plus phi. Okay, the calculation looks correct. This two terms will cancel out, so we'll basically have 1 over pi divided by square root of phi times 1 plus phi. So I guess this is the option which is closest, but it is not correct actually. So this should be square root of phi and there should not be any square, so it should be 1 over pi times 1 over square root of phi times 1 plus phi. By the way, 1 plus phi is outside of the square root, and when these corrections are made, then the second option is the correct one. Okay, this is something we have already discussed in one of the previous assignment questions, so I won't go into much details. So basically xt is a white Gaussian noise with zero mean. Xt is white Gaussian noise with zero mean. So white part basically says that xt and xt plus tau are uncorrelated for any non-zero time shift tau. When I try to convert these statements into mathematics, it will become xt plus tau is equal to 0 for tau not equal to 0, and only times the, by the way, this is the autocorrelation, and only times it's non-zero is when tau is equal to 0. That is, I am basically correlating xt with itself with no shift, and it is given by eta over 2 Dirac delta. Eta over 2 Dirac delta. Okay, so therefore we can write our autocorrelation function as follows: eta over 2 Dirac delta, and when you take the Fourier transform we obtain the power spectral density you can actually do the math here. So that is Rx tau e to the power minus j 2 pi f tau d tau integral minus infinity to infinity. So Rx tau is equal to eta over 2 Dirac delta, so it becomes just eta over 2 minus infinity to infinity Dirac delta times 2 pi f tau d tau. We know this integral is going to be 1, so we are left with eta over tau, and this is over the entire frequency spectrum. So the power spectral density is given by this here, eta over 2. So we next move into our this question, which basically shows a white Gaussian noise is given as input to a low pass RC filter. So what is the probability density function of the output? Okay. So your xt is a white Gaussian noise. You are passing it through a low pass RC filter, low pass RC filter. You are obtaining some other process yt. So what is the probability density function of the same? Okay, so if I am to draw a low pass RC filter, it's something like this. R here, and the capacitor here. So this is C, so therefore its impedance is given by 1 over j omega c. So basically you can see at low frequency it offers very high impedance, so the entire voltage entire signal applied here is come across here also, that is this is yt here output. And when you have very high frequency, basically this act as a short circuit, so the signal is 0. So basically it prevents high frequency component from passing and only let pass the low frequency component that are close to the DC values. Okay, so if I try to compute the functions here, first of all, this low pass RC circuit, you have to understand this is a LTI circuit, linear time invariant circuit. RC filter is a linear time invariant circuit. So basically it's like equivalent to passing through a LTI system. So if I take the frequency transform of xt and yt both, so let's say xt as a frequency transform of x omega and yt has a frequency transform of y omega, then you can see y omega is 1 over z omega c divided by 1 over z omega c plus r times x omega, right? So y omega divided by x omega is equal to 1 over 1 plus j omega rc. Okay, so this is what my transfer function is. So this is like equivalent to passing xt through a LTI system and obtaining yt with a transfer function of hf, right? And we have already seen in one of the previous question in details that if you when you pass through a signal through an LTI system, white Gaussian noise pass through an LTI system, and the output is also white stationary. Not only that, it's also Gaussian, and most importantly it has a power spectral density, that is Sy of f is given as sorry, now we are talking in terms of omega, so let's talk about in omega here. Omega is Sx omega times h omega whole square, that we have found, and we already have this expression h of f or h of omega, you can write both way. So that is given as 1 over a plus j omega r c, right? So therefore absolute value of h omega square is nothing but 1 over a square plus omega square r square c square. If I am to write it terms of f here, so that means omega is written as 2 pi f, so we'll obtain a square plus 4 pi square f square r square c square. And what is the Sx of omega or f, whatever it is, power spectral density of x here, because x is already mentioned as a white Gaussian noise, right? So its power spectral density is going to be eta over 2 in a standard notation over all the spectrum, that is absolute value of f less than equal to infinity, that covers the whole range minus infinity to infinity. So we have the power spectral density of y, this is phd of y as eta over 2 divided by a square plus 4 pi square f square r square c square. Now what is the energy of y here? This is the energy of y, right? Sorry, this is the power of y, and it is given as the power spectral density integrated over the whole spectrum minus infinity to infinity. So let us try to find its value. This is minus infinity to infinity eta over 2 a square plus 4 pi square f square r square c square df. This we can write as we can take common 4 pi square r square c square, so eta over 2 divided by 4 pi square r square c square minus infinity to infinity 1 over a divided by 2 pi rc whole square plus f square df. So I'll introduce a new slide here, is equal to eta over 2 4 pi square f square r square c square. We have the standard tan inverse expression here that we have already seen in earlier case. We have 1 over a here, so that is 2 pi rc over a, 2 pi rc over a times 2 tan inverse okay, I'm making one mistake here, not 2 here, it's tan inverse, it's just a moment, x, so f over 2 pi rcf over a, okay, 2 pi rcf over a from minus infinity to infinity. So this will become eta over 2, okay, made one mistake here, it should not be f, there is no f here, so it's 2 pi rc a times tan inverse of infinity, so that is pi by 2, and minus infinity, that is minus pi by 2. So we'll have pi here, so it's eta over 4 pi r c a times pi, so it's eta times 4 a r c. The way did I make some, okay, a value is 1 here now, sorry about that. Here what I am writing a, it should be actually 1 everywhere, so it's 1 1 here, 1 here, and okay, there should not be any a, okay, now it's good, eta over 4 rc, so that is what the power of yt is, eta over 4 rc. Now remember, we have obtained that when a white Gaussian noise is passed through LTI system, yt is also a WSS. So yt WSS means this is nothing but the autocorrelation function of y evaluated at 0. Now xt is already mentioned as 0 mean, so your yt we have already seen from this expression, if you remember, what is that, just a moment, yeah, this slide here you can see mean of yt is mean of x times this integral, and since the mean of x is 0 itself, so mean of y is also 0, so we'll use that here. We'll use that here, yt is also 0 mean. And what is the variance of yt then? If you remember the variance expression, sigma y square, it is given as expected value of yt minus mu y whole square. Now since mu y is 0, it is nothing but expected value of yt whole square, that is eta over 4 rc. So if I talk about y is WSS, it's also Gaussian only, since it's a Gaussian noise that is being passed through an LTI filter, so it's a Gaussian with mean 0 and variance eta over 4 rc, that is sigma y square. So it's a Gaussian with 0 mean and variance sigma y square. So if I am to write the PDF of y, it is going to look something like this. If I write in terms of a standard Gaussian, 2 pi sigma y square e to the power minus y minus mu y whole square divided by 2 sigma mu square. Now I just put the values. This is square root of 2 pi times sigma y square is obtained as eta over 4 rc to the power minus y minus 0 square divided by 2 times eta by 4 rc. So this will obtain as square root of 2 rc divided by eta pi e to the power minus 2 rc y square divided by eta. So this is the PDF of the yt is going to be, which is obtained by passing the wide Gaussian noise x through a low pass filter. So let's check which one of the answer matches. So 2 rc over pi n pi eta, sorry, okay, the fourth one is matching, so this one is the correct answer. Next is kind of trivial, so I'm not just going to solve it, it's kind of evident. Okay, this one is something interesting, and this one is from, I think, from a brief refreshing question based on the quantization level. So the structure remains same. We are given the probability density of the message sample. So we have message samples, which we denote as m, whose PDF is given as follows: 4 over 3 1 minus m cube, where 0 m 1. So what is the optimization level corresponding to the interval 0 and 1? So how do you obtain that? So the formula is as follows: optimal quantization level for interval a b. I'm just writing the generic formula here. A b, these are the integral limit fm m times m dm, that is the average of the samples in that particular integral divided by the probability that the message being in that integral. sorry, provided the sample being in that interval. So this one is the average value of sample in given interval, and this here denotes the probability of the sample being in that interval. So this ratio is give you the optimal quantization level. So if I put the values here, the interval is 0 to 1, 0 to 1, 4 by 3, 1 minus m cube m dm divided by 0 to 1, 4 third, 1 minus m cube dm. So I'll take another slide here. So you obtain 0 to 1, 4 by 3, 1 minus m cube m dm, and only 0 to 1, 4 by 3, 1 minus m cube dm. So this is 4 by 3 remains outside, 0 to 1, m square by 2. Okay, I will just signs are a bit misleading here. So this is m square by 2, this interval, minus m to the power 5 by 5 in this interval 0 to 1. Similarly here we'll have 4 third common, m 0 to 1 minus m to the power 4 by 4, 0 to 1. So in the top we'll have 4 third 1 over 2 minus 1 over 5. Here we'll have 4 over 3, 1 minus 1 over 4. So we cancel out both of them. Here I will have 3 over 10 divided by, here we'll have 3 over 4. So we'll have 4 over 10 or 2 by 5. So for this given probability density function, the optimal quantization level corresponding to this interval here is 0, is 2 over 5. Remember this one thing, that the quantization level corresponding to the same interval will change based on the probability density function. For example, had this been the uniform interval, you can do the calculation as a part of homework. It will become as the midpoint, that is the 0.5. But for this particular probability density function, which is a bit skewed, you can see that optimization quantization level is not 0.5 but it is actually 2 over 5 or 0.4. So based on the probability density function, your optimal quantization level will keep changing, but if you know the generic formula of finding the optimization quantization level in any interval, that is this, then you won't have trouble finding any. So with this I would like to conclude today's session. So it's a good time to ask any questions if you have regarding today's discussion. If you don't, I will just conclude the session. Okay, I'm concluding the session then. Thank you all.